Good day, students. Today, we shall look into a few more types of lasers, in particular, diode lasers and NDYAG lasers. Now, this is the picture of a diode laser. It is a specially fabricated PN junction device that emits coherent light when forward biased. So, basically, it is just a PN junction diode and it emits coherent light when it is forward biased. Now, it was first fabricated by R. N. Hall and his co-workers in 1962. Now, it is very similar to the working of an LED, but the LED emits incoherent light, whereas the laser diode emits coherent light. Now, an example for a diode laser is the gallium arsenide laser. It emits light at the infrared wavelength of 900 nanometers. Now, this picture shows the design of a diode laser. It essentially consists of three components. They are the pump source, which is a high voltage power supply, a heavily doped PN junction, and metal contacts towards these junctions. Now, this is the schematic diagram of a diode laser. Learn to draw this schematic diagram. Now, let us look into the working of this diode laser. So, in this, a P-type semiconductor is joined with an N-type semiconductor to form a PN junction. Now, this junction allows the electric current in forward bias condition, whereas it blocks the electric current in reverse bias condition. Now, when a forward bias is given to this PN junction or diode, now the free electrons from the N-type material will move towards the P-type material, where we have excess of holes. The electrons recombine with the holes. Similarly, the holes from the P-type material will move towards the N-type material, and there it will recombine with the electrons there. Now, because of this flow of charges, we can get electric current from this junction. Now, in the energy level diagrams shown here in the top figure, we can see that before bias is given to the junction, the Fermi level is constant, and hence the electrons and holes have difficulty to recombine with each other. But when forward bias is given to this system or to this PN junction, the Fermi level is redistributed. Hence, the electrons in the conduction band will be able to move into the valence band. Now, when a DC voltage is applied across the laser diode, so these electrons will move towards the p-type to recombine. Well, some of the electrons will recombine with the holes and they release energy in the form of light. So this chance emission is called spontaneous emission. Now, the photons generated due to this emission, spontaneous emission, they will travel through the junction and it will stimulate other electrons to recombine with the holes. Now, as a result, more photons are released, and this process of photon emission is called stimulated emission. The light generated by the stimulated emission will be parallel to the junction. Now, the two ends of the laser diode junction are optically reflective. That is, one end is fully reflective, it is mirror coated, whereas the other end is partially reflective. Now, the fully reflective end, it will reflect the light completely, whereas the partially reflective end will reflect most of the light and allows a small part of the light to pass through. It emerges as the laser light. So, the light generated in this PN junction, it will bounce back and forth between these two reflective surfaces. Hence, an enormous optical gain or amplification is achieved. The light generated due to the stimulated emission is escaped through the partially reflective end of the laser diode, and it produces the narrow beam of laser light. So in the case of gallium arsenide diode, we get a red light of wavelength around 900 nanometers. Now next, let us look into the NDYAG laser, neodymium YAG laser. So NDYAG is actually the acronym for neodymium yttrium aluminium garnet. This laser is a solid state laser. The lasing medium is a solid crystal as shown on the right, and here NDYAG is used as the lasing medium. It is a 4-level laser system. It operates in both pulsed mode and continuous wave mode. Now this NDYAG laser generates laser light commonly in the near infrared region, that is at 1064 nanometers. It also emits laser light at different wavelengths like 1440 nanometers, 1320 nanometers, 1120 nanometers and 940 nanometers. In this, the most popular wavelength is 1064 nanometers. Now, the NDYAG laser consists of 3 important elements: the laser medium, that is this crystal, the pump source, that is this flash tube, and the optical resonator, that is this elliptical cavity. Now, the laser medium or the active medium is made up of the synthetic crystalline material yttrium aluminium garnet, where it is doped with the chemical element neodymium. The lower energy state neodymium ions are excited to the higher energy state to provide the lasing action in this active medium. So the participating electrons or ions are that of neodymium. Now in neodymium YAG lasers, light energy sources or pump sources are flash tubes or laser diodes. It supplies the energy to this active medium. The optical resonator here is an elliptical cavity, and it has 2 mirrors on either ends. These mirrors are silvered or optically coated. One is fully silvered, whereas the other is partially silvered. Now, to understand the working of an NDYAG laser, we should know its energy level diagram. Here, we can see 4 energy levels participating in the lasing action. E1 is the lower energy state. From here, by absorbing light from the flash tubes or laser diodes, atoms are excited to the pump state E4. Since the lifetime of E4 levels are short, they release non-radiative energy and fall into the metastable state E4. Here, the lifetime being longer, atoms accumulate here. Hence, we achieve population inversion. Now, at that time, by any chance, if light is emitted towards the lower energy level E2, that will be a spontaneous emission. But this spontaneous emission can trigger the other atoms accumulated in E3 to stimulately fall towards E2. This is called stimulated emission of light, and that will be in the wavelength of 1064 nanometers, depending on the difference of these 2 energy levels. Okay. Now, it is a 4-level laser system. Hence, we have 4 energy levels participating: E1, E2, E3 and E4. Now, when flash tubes or laser diode gives energy to this active medium NDYAG crystal, the lower energy state neodymium ions, it gets enough energy to move to the pump state E4. Now, the lifetime of this pump state is very small. Hence, after a short time, the excited ions will fall into the next lower energy state. This is a metastable state E3, and they move to E3 by releasing non-radiative energy. That is not emitting light, they will give energy by heat or by phonon interaction. Now, the lifetime of the metastable state E3 is high as compared to the lifetime of pump state. Hence, the electrons, they reach E3 much faster than they leave E3. So, this results in the increase in the number of electrons in E3, and hence population inversion is achieved. So, after some time, now these electrons or ions in the E3 state will fall to the next lower E2 state by releasing light. This chance emission of light is called spontaneous emission because its lifetime is over. That is why these set of photons, initial photons, are emitted. Now, when this photon is emitted due to spontaneous emission, it interacts with the other metastable state electrons or ions, and it stimulates that electrons or ions to fall to the lower energy state. So, two more photons will be released, and this emission is called stimulated emission of radiation. Now, this light generated in this active medium, it will bounce back and forth between the two mirrors on either ends. It again further stimulates other electrons or ions to fall to the lower energy state by again releasing light. Now, the light generated within this active medium is reflected many times between these mirrors. Hence, it gets amplified, and further it escapes from the partially reflecting mirror as the narrow beam of laser light. With that, we shall end this session. Thank you.